Great, everyone. We're going to get started in a few seconds. Please make your way to your seats. I'm your program chair, in case you haven't noticed. Just two small announcements. Do download the conference app. We use it to provide some form of communication, tell you about any last-minute changes, invite you to the amazing inaugural ECAI social run. Has anyone here registered for the social run? I can't wait. Wednesday at 8 a.m. It's a great way to stay fit and active before the last day of the conference and to see some of Krakow's amazing sites. And you don't need to run. You can also opt for a walk. So registration is right in front of the registration desk. Just tell them you'd like to sign up for the social run. It's a great pleasure to introduce our first invited speaker, Professor Gal Chechik, Professor of Computer Science from Bar-Ilan University. Gal studied his PhD at the Hebrew University, and then he postdoced with Daphna Koller, if I'm not mistaken, at Stanford. I think what really sets Gal's work in machine learning apart and why we've invited him today is that he doesn't only consider and attack important basic research questions like generalizability and like applications, but he also cares a lot about industry, and indeed Gal is head of Israel's NVIDIA research office in Tel Aviv. So without further ado, let's welcome Gal. At the end of Gal's talk, you can already sign up here in the two mics for questions. We'll take a few questions at the end. Gal, the floor is yours.
Thank you. Hi, everyone. First, thanks a lot to all the organizers, the scientific committee, and especially Kobe for having me here. It's a real pleasure. And also the organizers, the administrative staff, Camila, and everyone. It looks like an amazing conference. This is the first time I'm speaking at the three-stage stadium. I'm about to burst singing, but I should stop myself about that. So today, I'm going to talk about personalization of foundation models for visual generative AI, text to images. So if we take the text and try to depict it with images, we're going to take the foundation models, combine them with our data, and we're going to discuss how you do this combination to create high-quality, personalized models, beautiful churches like this. So let me start with talking a bit about foundation models, and they are interesting because they made a big change in how we do machine learning. The classical workflow in machine learning was, as you learn in Machine Learning 101, you collect your data, you annotate it for your task with labels that you care about, and then you train your model for that task, and then you deploy and infer on data for your task, for your specific task. And in foundation models, the workflow has changed. You start by collecting a huge data set, and this data set may be sometimes unlabeled. And then your goal is to learn a representation from this huge data set, basically learning the prior distribution over the relevant data that you have. And if your data is unlabeled, sometimes you use self-supervised learning that I'm going to talk about in a second. And now the point is that once you learn that representation, you can later use it for other tasks, downstream tasks. Many of them could be things that you haven't even thought about when you trained your foundation model. So let's talk about self-supervised learning for a second, because this is kind of the main vehicle for foundation models. The idea is that you train with unlabeled data and you use supervised learning. So supervised learning with unlabeled data. How do you do that? Well, you take your unlabeled data and you define an auxiliary task for which your labels are known. Then you use it to train a representation for that auxiliary task. And it turns out that often this representation is useful, of course if you're lucky, for downstream tasks. So here are two examples. First one, imagine you have a large set of images like this dog here. You can take these images and corrupt them in some way. For example, remove the color or crop it or flip it and do a lot of distortions to that. And now you try to learn an encoder that maps images into some representation. And what you want is that images and their distorted or corrupted version would be close in that representation. They should be similar. And this would capture some of the semantics of the problem, even though you did not use any specific labels. You don't know this is a dog. And turns out, even though you're just removing kind of simple distortions, perhaps low-level visual appearance distortions, actually these models learn a lot about the semantics, and the representation that you learn are often very useful for tasks after that, like training a classifier on top of that, etc. Here's a second example, which is similar in nature. Here, again, you take an input image and you mask some patches of that. This is called masked autoencoder. And here, what you do is you take this masked image and, again, you learn a representation from which you can reconstruct or decode the original image without the mask. Now, again, this is a low-level task, but it turns out that the model learns a lot about how images look like, how birds look like, how all classes look like. And this representation that was learned, even though you have never used any high-level labels, it captures a lot of semantics in the problem. So this is self-supervised learning. I want to talk today a lot about vision and language. So let me highlight one foundation model that how many of you have worked with CLIP or know about CLIP? I guess, yeah, a large part of the audience. So the idea, and this is an old idea, CLIP is just the recent and most effective implementation of that, is that you want to create a joint representation of visual content and text content. So you want to have an encoder that takes an image and maps an image into that joint space, and another encoder that takes text. It could be just single labels like here, or it could be much richer text, long descriptions of images. And of course, you want to create the representation such that images are mapped near text that matches them. So how does CLIP do that? Well, they train an encoder, a text encoder that takes a description, and an image encoder that takes the image, that pulls together images close to their text encoding. And at the same time, they push apart images from descriptions of other images in the batch, or from other images in the batch, and other text in the batch. So this is why it's called contrastive learning. You pull what's similar, you push away what's not necessarily similar. And turns out that this learns a really useful representation. Once you learn this representation, there are a lot of applications that you can use the representation for. Just one example, you can do classification with that. Given an image, you map it to the space, and now you go over the set of candidate labels, cat, dog, and everything, and you just do nearest neighbor, and you find the closest label. That's very natural to do, but it turns out you can do much more elaborate tasks with that. People show you can do open vocabulary zero-shot image captioning, like describe image with a rich language in a discriminative way, or you can do text-driven segmentation and detection, and the list goes on and on. This is a very useful model. I'm going to use it in my talk in the next several chapters. So we talked about foundation models. I want to talk a bit about visual generative AI, or how we generate images from text. Again, how many of you have played with text-to-image, things like Midjourney or DALL-E? Yeah, almost everyone, right? It's hard to avoid that in the past year. And these models really generate like fantastic, amazing images. Some are fantastic, some are realistic, really very interesting way to create visual content. Let me explain how they work. Actually, the idea is very simple. So here's the point. You start with an image, let's say this kitty here. And what you do is you add noise, just random per pixel Gaussian noise, independent per pixel. And then you add more noise and more noise. And of course, when you add, after many of these steps, you end up with an image that is just completely noise, right? The signal has completely washed away. So here's the self-supervised part of that procedure, you pick just a pair of images. Let's say this one. You have one which is more noisy and less noisy, and what you're training a deep network with a UNet architecture that takes a noisy image and removes some of the noise given a text prompt. And now you just repeat that process. You sample pairs of images, you know what the output is because you generated that, and you train a model, a deep network, to take a noisy image and remove some of the noise. And at inference time, you just repeat that. You just sample this high-dimensional multivariate Gaussian, and you, given the text prompt, denoise and denoise and denoise and denoise until you get a nice image. And if you don't like it, you sample again in this noise. This is why when you in Midjourney or something, when you repeat the same generation, you get different images, right? Because you start from a different random seed. So it's a simple, of course I skipped a lot of the details. There are two details I want to mention because they might be important for this audience. First, of course, everything is not done at pixel space. It was a bit misleading what I showed you. You actually take images and you, where is it? Okay. You actually take images X and you use an encoder to map them to some latent space, which is lower dimension, 64 by 64 by 4. Also, there's an important component called the cross-attention map. And this operates like an attention component with a key and value and query as in standard attention architecture like transformers, but it is cross-modal attention. So for every word in the sentence, it basically tells you which pixels attend to that word. So it gives you kind of a spatial map of the influence of a word in the sentence. Okay. So this was about foundation models, and they're great. They were trained on tons of data over the internet or owned data. But now, what about our own data, right? We're used to train models, and we care about our own data. The question is, how can we take these models and teach them or help make them handle our own content? And of course, you don't want to wash out all what they know. You want to keep their prior knowledge about how images look like, but you want to combine that with your personal data. And this is the topic of my talk. How can you take a very complicated model that has some prior about the distribution of data and combine it with a much smaller data set in a way that would leverage the prior knowledge, but for your specific data? Now, just a side comment, I'm using here the word prior in a very loose sense. This is not the Bayesian probabilistic prior, because these models, we do not have proper calibrated distributions. So it's a prior in the loose sense. So let me just motivate for a few seconds why we care to generate things about our own data. So either generate or discriminate. So for discriminative models, here are several use cases, right? So this would be for personalization in visual analysis. Imagine that you have your photo album and you want to search for items that are yours. You want to search for that photo where I was with my red bag at the park, with my red bag, right? Not a generic red bag. Perhaps you want to search in a video for an item or in inside an image to locate an object. Or perhaps, think about a few years from now, we're going to have smart devices in our home. Some of us already have, right? You have a smart vacuum cleaner, perhaps you have a smart car, and we would like to interact with it in natural language. And once you have your smart devices, you want to refer to your items, right? So if you have a smart robotic hand at home, you want to, make me coffee in my favorite mug, not just a generic mug. So you need to teach them personalized objects. This sounds too futuristic, but I think we might see that not too far away. What about generative models, generating images? So here are a few cases. On the left here, this is my dog Max. He's a beautiful dog, not that smart, very stubborn. But anyways, So you know, with diffusion models, you can generate images of a dog wearing glasses. Well, I want to generate images of Max, with glasses, not just a generic dog, right? I want images of my family members and my pets. This was for a consumer application. Think about a business application. Imagine that you own a toy company, and you want to have an ad campaign for this teddy bear that you manufacture. So now you would like to advertise your teddy bear, not a generic toy, right? So design an ad for my teddy product. Finally, think about an internal designer. Perhaps you want to design a room, and what can you do? You're stuck with this sofa from Grandma Rachel and that you cannot get rid of, right? This must remain in the house. So how do you design a room or a house with specific furniture? So let me show you results from a paper that came out about a year ago, and we presented that in ICLR about half a year ago. It's called textual inversion, or an image is worth one word. So here's how it works. You give the model just a handful of images, and this is our image of some sculpture that a student had that in the lab. And what we're going to do is we're going to teach a new word to the vocabulary of the model. So the same way they have, statue and every word in the vocabulary, now they have one more word in their vocabulary, which we just denote as S star here. Now, once you taught this word, I'm going to explain in a second how we do that. Now you can use it with any other word in the vocabulary, right? So you can ask for an oil painting of S star, or an app icon of S star, or Elmo. This is my favorite. Elmo sitting in the same pose of S star. This statue doesn't have, the head is laying here, but Elmo got his head back. Or a crochet S star. So you can see it really can do interesting combinations of your personal content with all the prior knowledge that it has. Here's just another example. This is this striped cat. You can generate a themed lunchbox, an S-star themed lunchbox, or a Banksy art of S-star. So how does this work? How do we do that? Remember, I told you about clip, and in clip, every word is represented as a vector in the representation space. What we do is basically find that representation for just a single word. So we are just going to learn the vector representation of this new token. So if you say a photo of a star, you're going to map this to this vector that we're going to find. This is what we optimize over. And we optimize it over such that it obeys the following property. If you take the training images, you noise them, and you denoise them with that sentence, you get something that is similar. The generated image would be similar to the training image. And similar is just reconstruction loss in the latent space, not in pixel space. And now you repeat that many times, and basically you just learn a single word in that space, just 1,000 numbers. Before I go on, I want to highlight some, I think it's interesting properties of this model. So here's, focus here on the teapot on the right. These are the original images of the teapot, quite a colorful one. And these are images generated by our model, a photo of S star. Now, these are not identical to the teapot, right? The handle is different, it's black, it's slightly, it's not exactly the same size. But it's really surprising how well it captures like the visual essence of what this teapot is about, right? And remember, you only learn a very small vector. So it looks like that if you already have a big model that knows how objects look like, you can learn new concepts with a relatively small number of parameters. Actually, we can quantify that. We can ask people, we show people this, and if I've shown you this very quickly, you'd think it's the same. And you show raters and ask them, and they say that the internal variability inside the ground truth images is about the same as the variability between ground truth original images and the generated ones. Now, of course, by the way, this is just another way to control the generation. You control it with these images. If you want to control similarly with text, of course you cannot do that. We ask people to take that teapot describe it in text and then used text-based generation with no training of the images. And of course, you get something very different, right? They are not similar to this at all. So these were examples, but of course, there's a question of how do we systematically evaluate and quantify the quality of these personalized models. So I want to highlight how we think about this problem. So there are two important properties first. One is visual fidelity, right? How well do the generated images match the visual examples, the 4 or 5 images that we give for training? Then there's editability. There's a question of how well the generated images match the text prompt. Now, be aware that there's a tension between the two, right? It's a contradictive trade-off, because if you want something to obey the text prompt might take you very far from the original image. So one way to think about it is kind of a Pareto front. Oops. A Pareto front where you have these, can you see my slide? Okay. Where you have matching of the text prompt and matching of the original image, and you care about the kind of Pareto front in this trade-off, and you want to improve in both. And you can do that using CLIP, or you can ask people to evaluate that. This is, by the way, our approach, which is somewhere high in this Pareto front. Besides these two quality metrics, there are other things that's important for us. First, you want to learn from small number of examples. And some of the examples I'm going to show you were trained with just a single training image. And also pretty important is compute. We want a low memory footprint. So every concept that we teach should only be stored as small as possible. And of course, we want training to be fast and inference to be fast. I should say that still in this field, having an automated evaluation metric and evaluation protocol is still missing. So if I encourage you people to think about how we can automate some of the evaluation process. So I told you about this very lightweight model, textual-inversion, just 1,000 numbers. And in parallel with our work, another work came, it's called Dream Booth, maybe you've heard of it. And they took kind of the opposite approach in terms of size. They basically fine-tuned the full model, the full unit. We were hesitating to do that because we thought, oh, you might overfit or might hurt the original model, but it turns out it's not that bad. It doesn't hurt the model, and you get something that is rich. It has many, many parameters, and you can edit a lot there. One caveat is that because you train the full model, for every concept, you need to store sometime up to 7 gigabytes, right? So if you want to learn a dictionary of concept, this becomes costly. So one approach that was proposed is that instead of teaching or training the full unit, you just train a low-rank version of that. So LoRA, it's a low-rank adaptation of the cross-attention layers. And since these papers came out, there's a series of papers, some of them like custom diffusion, train the K value and the K and V and the embedding. There are other variants that take a single image with multiple concepts, and there's a series of papers here that I cannot cover. But I wanted to highlight one idea that we wanted to improve these models, going beyond just doing smarter computation, low rank and everything. We started to look at failure cases, and here's what we observed. So on the left, you have the examples, this nice doggy here you trained with 4 images. And now we ask the model, textual-inversion, to generate a dog star. This is our new concept, right? It's a specific dog, not the generic dog. A dog sitting in the rain. And it didn't work very well. There is a dog. It's not exactly this one. But when you look at the attention for the word dog star, for our dog, you see it's all over. It's not localized correctly. So it seems like the model finds it hard to separate the concept from the background. But now here's the intuition. Well, these models, they would do that well for a generic concept, for a dog, not for this specific dog. So here's what we can do. We can generate with the prompt a dog is sitting in a range, just a generic dog, and then use the location of the generic dog, lock that, and regenerate while locking these pixels with the specific dog, right? So we keep the location where the dog appears, and this is controlled by the key in the cross-attention map. And we only edit the value matrix for dog. And this is what you get. When you do this, you get a nice localized attention map, and the image is also generated well. And this is with this key locking idea that you need to know what is the superclass. You need to know that this object is a dog. So this is an approach we call perfusion. You only do very slight editing. We also do it rank 1. So if you think about a few models that I described to you, Dreambooth, the original one, is just almost 10 gigabytes. 2 orders of magnitude below that is LoRa with maybe 10 megabyte. Perfusion is only 100, again, 2 orders of magnitude lower, 100K, but it is editable enough, and you can generate high quality images, and textual inversion is just very tiny, 1K. So just a few fun examples. So this is the teddy bear. These are the 3 images we use for training. And now you can, once you learn the concept, you can have Teddy dressed like a wizard and a samurai and a superhero. You can also teach this teapot, okay? A golden teapot and teapot made of clay or yarn. But now you can actually combine several concepts, which I found pretty fun. Teddy, this specific Teddy, is sailing in this specific teapot in the lake. Oops. And Teddy is engraved on a teapot. Again, this specific Teddy and this specific, I think this is cool. And of course, finally, I asked the team, I gave them some images of Max, and I finally wanted Max to educate. So I asked them to have Max reading a book. And you see he's really interested. And my kids were really excited to see Max reading. Finally, he's going to have some sense into him. And of course, you can have Max cooking a meal, painting of Max on a boat, photo of Max wearing a hat. I want to highlight a few other properties of this type of model. I stress the idea of this trade-off between matching the text and matching the image. And in some approaches like ours, you can, at generation time, decide, you have like a knob that helps you be more matching the text versus matching the image. And here, for example, so you get Max, and with a prompt an app icon of a dog. So on one hand, you have something that is more iconic, and you have something more realistic that matches the image better on the other side. And you control that at generation time. Here's also an interesting application for using personalization. You know that a lot of generation models, they might be biased if the data is unbalanced, and sometimes you want to rebalance the data. And there's a relatively easy way to do that with this personalization model. For example, if you ask, this is a baseline model, you ask for a doctor, you get images that are predominantly male. And if you take a relatively small set that is balanced, you can get more diverse in terms of gender and ethnicity. So here you have a photo, a star, generate something that matches better the distribution that you are interested in. Okay. So I want to switch gears. I talked about generation of personalized concept. And now I want to talk about a few other aspects of text-to-image generation and diffusion models that are closely related to personalization. And I'm going to highlight several issues. Perhaps you can spot one issue in these photos. So let me I want to cover 3 known problems. One problem is the following. This is what happens when you ask for a yellow flamingo with a pink sunflower, and the prompt just ignores you, right? You have a pink flamingo. The second problem is that when you try to generate rare objects like a payphone, you get something weird. And of course, hands are notoriously badly shaped. There's a lot of struggle. At some point, this was the easiest way to tell if an image is generated or genuine because no one could make fingers work well. Today, it's much better. I think the funniest example of that was I saw this image. Looks like a reasonable hand. Can you guess the prompt? Guesses for what prompt was used to generate this image? What's that? Okay, so the prompt was a hand with one missing finger. Okay. Okay, so let me talk about the first thing, and this is the problem that attributes and noun are not bound correctly. So again, you ask for a pink sunflower and a yellow flamingo, and you get the opposite. And the problem here is that the visual prior that the diffusion model has is very strong, and it just ignores the text prompt because flamingos are pink. And I told you, we're interested in how we take the prior from the data and try to combine it with our data. How can you do that? And this is just one problem. This leaking can happen to the other object or perhaps to the background of the scene. Or here, a horned lion and a spotted monkey. Lion has no horn, monkey has no spots. And in our approach, you get the correct color and, yeah, horns and spots for the monkey. So how do we do that? The idea is actually really, really intuitive. Imagine you have this text prompt, a red crown and a golden strawberry. So you parse, you just use standard syntactic tools. There's some sometimes subtleties there, but you find crown is modified by red and strawberry modified by golden. So you have these pairs that are connected. So now what we're going to do is we're going to, at inference time, at generation time, again, there's going to be no training, just at generation time, we're going to have one denoising step and one SynGen step. Iterative, right? Denoising step, syntactic generation step, right? One step like that, one step like that. So the denoising step you already know, that's a standard unit. Here's what happened at the syntactic generation step. Remember I told you that we have the attention map that tell you which pixels are relevant for every word in the sentence. So we know there's an attention map for red and attention map for crown, which want them to overlap. And we want them to not overlap the other attention maps of the other words in the sentence. And when I say overlap, we just treat the attention map as a distribution, and you compute the symmetrized KL diversion, the Jensen-Shannon diversion between the two distributions. So here's how that affects the image. On the left here, you see at the top left, this doesn't work, okay. On the top left, you see we start with the noise. This is maybe a few steps after the noise. And you see the attention map of red and crown and golden and strawberry, they're all overlapping. But then as you move more and more steps, you push red and crown to overlap and golden and strawberry to overlap. And then once they do that, you just stop this additional loss and you let the denoising model improve the quality of the image until you get this nice combination. And so there are a lot of qualitative examples. Sometimes with other approaches, it's really hard to, the visual prior really fights back. It's hard to generate fire hoses, fire hydrants that are not red, and a lot of things. And this approach does that well. We have systematic human evaluation with radars, and it doubled the accuracy compared to baseline methods. So this is a way where you can control some of the strong prior that the model has. About the second problem, I want to tell you about rare classes. So here, we talk about personalized, right? We have an instance, specific instance, which is really, really rare, right? It was never seen by the model. But now I'm going to talk about classes that are not very common. So the point is that if you take standard model like Stable Diffusion and you ask to generate common objects like gift and Jeep, you get something nice, but hands and oxygen mask and payphones, you get weird generated images. And our approach fixes that. So here's the observation. Here's how we quantify this observation. We took all 1,000 classes of ImageNet, and we asked the diffusion model to generate images for every class. Just a pre-trained frozen diffusion model. But now we measure the quality for every class using a pre-trained classifier, and we sorted the classes based on how frequent they were in the training distribution of the diffusion model. So the model was trained on a public data set called Lion2B, 2 billion images, and you just know how many dogs and cats, there are tens of millions on the left, and as you go to the right, there are fewer and fewer images for different classes. Oxygen mask and payphones are around here. And what you see is that once you go below 10,000 training images, this is the average accuracy, really falls. So these models, they're bad at generating rare classes. And now the question, why does that happen? So one possibility is that the model just forgot about them. It was overwhelmed by millions and millions of cats and dogs, and they're this catastrophic forgetting property. And the model just forgot about payphones and oxygen masks. But I showed you that you can learn a concept from like 5 images. 10,000 images is a lot. So we had the following intuition, hypothesis. We're thinking about this way. Remember the diffusion model, it actually receives a sample from the high-dimensional Gaussian distribution and a text prompt. And the intuition was that perhaps for cats and dogs, you sample this noise space very densely, so the diffusion model will never be surprised. Every seed in that space, together with cats and dogs, would be in distribution for the diffusion model. But perhaps for those classes that are at the tail, perhaps for some areas, it would be an out of distribution for the model. So maybe the memory of oxygen mask and payphones is there. You just need somehow to extract these repressed memories. You need to hypnotize the model and extract these repressed memories. So the idea was to do exactly that, to find areas in the latent space, in the original noise space, that would generate correctly images that you care about. So you take a few training images like we did before, and you find areas in the noise space that would yield these type of images. And here we had 2 losses. One is actually in the latent space, reconstruction in the latent space about the appearance. Another was a more semantic distance in the clip space. Now, once you found these areas in the latent space, then you can find their centroid, and you can sample around the centroid of these samples. And this works surprisingly well. Remember, all you do is just select a starting point. And we have reasonably looking hands. We have a lot of tail examples. These are the training images. This is a baseline, and this is our images. And their quality is much better. Of course, we evaluated that in a systematic way. You can, again, run a pre-trained classifier, and you can see it went up from this red curve to this blue curve. The classifier can correctly identify or understand what these images are about. And this also holds in long tail and few-shot learning. We also ask people to evaluate how these images look like, and they prefer these images both in terms of how well they match the prompt and look similar to examples from that class, and also how realistic the visual appeal of the images. And once you have that, this is actually helpful for things like semantic augmentation. Imagine that you want to train a classifier, but some of the classes, you only have few samples. Now what you can do is you can use the diffusion model to generate more samples from this class. It would not memorize, it would not give you the same images again, because it has all these priors. It would change lighting and shape and context, and you'll get a larger data set, and you can use that, and you get the new state-of-the-art on long tail and few-shot benchmarks. I should mention here evaluation here is very tricky because we want to make sure that there's no leak of information from the test set that perhaps the models have already seen because they are online. So we believe we did very careful evaluation of that. So an interesting technical point, I think. I told you we're looking for the centroid in this space. And it turns out finding a centroid in this space is tricky. It sounds simple, but it's tricky because images in this space are sampled using this high-dimensional multivariate Gaussian distribution. So just a few words about Gaussian distribution. I think we have a mental image of Gaussians looking like this, where all, in one dimension, most samples are close to the center, also in 2 dimensions. But when you go to high dimensions, actually, because you have so many dimensions, most of samples are far from the center. And if you look at the distribution of the norm, the distance from the center, it is very narrowly distributed, in this case, around 128. So almost all images have, they're like on a sphere far from the center. And this is a well-known fact. Many of you already know that. But what this means is that if you are about to find a centroid in this latent space, then you should be careful, because if you want to find a middle point between Krakow and San Francisco, of course you should not go through the core of the Earth, you're going to get burned, right? So there's a question if you have, I'm not showing here high dimensional, but this is 2-dimensional illustration where you have things around the sphere. So if you want to interpolate between these 2 points, of course you cannot do linear interpolation, you get very bad images. What people do is sometimes called a spherical linear interpolation. Basically, you linearly interpolate across angle and linearly across the radius, but this also doesn't work very well because sometimes you overshoot, sometimes you undershoot. Our idea was to treat that as a maximum likelihood problem. What you want to do is to find the path such that the integral over the path has the highest likelihood based on the underlying distribution. And it turns out that this defines a metric induced by this distribution in that space. And now, when you have this distance, you can find a centroid, and a centroid is just the point that is closest in terms of the likelihood-induced distance, this centroid from all these 3 points. And when you do that, again, all the results I showed you keep improving. So I told you so far about text-to-image, but I want to tell you about the next steps. Because generating visual content is not limited to still images. There are efforts around 3D. This is like a real 3D volumetric model, video, and virtual simulated worlds. And let me talk quickly about each one of these. I want to tell you about an approach called Dream Fusion by Poole et al., which is a really clever idea how to leverage 2D like still image generation models to generate 3D objects. Here's how it works. You start by a model of a 3-dimensional object. And these models, basically, they are given a point in space and they tell you the appearance there, right? The point in space and the camera position, they tell you how it looks. And this is parameterized with a neural network, like a multi-layer perceptron. So here's what you do. And I'm skipping a lot of the details, but can you see this is the 3-dimensional model, and you render that, you get an image. You take that image and you add some noise to that. And now you feed this noisy image to your diffusion model, to your unit. And that model removes some of the noise conditioned on a text prompt, a DSLR photo of a peacock on a surfboard. Now, you take what you generated and you look at, you subtract the noise, and this gives you what has changed by the model from the original image. So what basically this measures is what should change in the image to make it fit the prompt better. So now you can use these changes and feed them back, propagate them back to the model, to the 3D model. And because everything is differentiable, so you back propagate these gradients. And you repeat that, and then you get an object that fits your text prompt. And there are a lot of very nice papers generating new 3D objects from scratch based on the text prompt. I want to connect that to personalization. And this is related to a really common problem that imagine that you have, when you want to collect data about 3D object. You have an autonomous vehicle traveling in the street, and they have this LiDAR that collects points on parking cars nearby. Of course, you only see one side of the car. And what we would like to do is to complete the unobserved side of the car, the dark side of the car, okay? So this would be the input on the left, these blue points, and on the right is what you complete. And our idea is the following. You take as input this point cloud of sofa, and the text saying a sofa, and you can use this loss, the diffusion model loss that I just described to you, on one hand, to make the generated object match the prompt, but you also want it to obey the origin point cloud. And here there's a bunch of clever losses that you can use. Of course, you want the object to match every point that you see, but also, if you don't see a point, you know there's no volume there. So there's negative and positive constraints, and when you do that, you can get, here's an example. This is the input. You have just the handle of this tool, and a teapot will give you this, a coffee pot, etc. Now, baselines in this area were trained on data sets of chairs or tables, and they complete well chairs and tables. Of course, they do poorly when they are asked to complete something from different classes. But it turns out that this approach actually works about the same, about as well, for known classes as the other approaches. So you gain for new classes and you don't lose for existing classes. So this was for static objects. There's a lot of interesting work about generating virtual worlds. On the left, there's work on generating scenes, a 3D from a diffusion model that learns the statistics of, maybe Silicon Valley neighborhoods. On the right, you have a NERF where this is instant NERF. You get a very quick 3D representation just from a small number of 2D images. You reconstruct a 3D object. But I want to talk about perhaps the next step to that. What we want to generate at some point would be virtual worlds. That is, you want to have a physical simulation, and in that physical simulation, you want agents that actually behave in that environment. So here's a recent work we had at SIGGRAPH. The idea is that you use motion capture to teach the model some type of movements, like crouch walk and a kick and roar, and you map all of them to a latent space in which you can move between these and interpolate them. And now you can have a sequence of natural movements. What you are going to do is you're not going to generate the video of this, but you're going to train a reinforcement learning agent that control that avatar. So here's an example. So here you have an agent that controls the actuators of this animated character, and it can do a lot of nice things. And now you can control it with this high-level task, right? Move right toward the target, slash, celebrate, yeah. So there are some challenges here. First, you want to make sure that the movements look natural. So you train a low-level policy that is in agreement with the motion capture data, with the mocap data. Then, in parallel, you have a high-level policy to control the goal, right? To go to that post. And once you train these two things, at inference time, you can give it new instructions or have slightly different objects, and the controller in real time, of course, solves the task and behaves. So I told you about foundation models and how to personalize them. We talked about text-to-image models and several different problems there, and about the next steps of how you do personalization and use strong priors about distribution of visual content to generate things in 3D and in virtual worlds. So I want to thank, I had many collaborators in NVIDIA and the Technion and Tel Aviv University and Bar Ilan, of course. I also want to thank you, and I want to encourage you, if any of this is interesting to you, please come and talk. We love to collaborate. I'll be around for today and tomorrow, especially for a young student. Don't be shy. If this is interesting, come and chat. It's always fun to talk. And thank you, everyone.
Great. Thank you so much for a brilliant talk, Gal. We have some time for questions. If anyone wants to ask Gal questions, please come. You can come up straight to the mic. And while we're waiting for people, I'll just get the ball rolling. I'm really interested in kind of taking your work maybe into an applied setting, and I'm wondering if you've ever considered that, whether education or another kind of setting.
Yes, I think so. I think the world was swept by large language models, ChatGPT that everyone played with, and of course, this model now become aware to visual content. GPT-4 combines now, vision and language, and clearly, every intelligent application is education, medicine, a lot of application. You need to do reasoning that is grounded or embedded in real, in visual content or grounded content, not just text. I can say in terms of application, some of the papers that I showed here, we are working to put into products at NVIDIA. So I hope people can use that at some point.
So Gal, thank you for a truly inspiring talk. Fantastic. I particularly liked your talking about personalization. That obviously is an important topic. But maybe there's a level in between, sort of, fully general and fully personalized. And I guess what I'm hinting at is sort of, adaptation to cultural biases and preferences, right? And so looking at where and by whom many of these models are currently trained, at least the commercially available ones, right, or the broadly available ones, one could wonder whether there aren't areas such as education, medicine, for example, where, the world from a European perspective looks very different, without putting any value to that, by the way, from the world in the US or in China, for example, right? And so I'm curious whether you could comment to which extent personalization techniques do you think can also sort of, bring cultural adaptation as it might be needed to the language and to the visual, and more importantly to the combined world, right? Because in the end, these are in some sense world models, and you make them even more so in the steps that you outlined now. Thanks.
Thank you. This is a really important question. First, I totally agree that when I say we'll learn about the distribution of visual content, of course there's no single distribution. And one of the wonderful things of humanity is that there's a diversity, and different cultures have different distributions, perhaps. I think to handle this, we should start from the basic infrastructure. And there are several papers that try to build from the ground up, to build CLIP for, the visual language representation for other languages. I can tell you that we are interested to look for a CLIP for Hebrew, for example. For those of Hebrew speaking in the audience, if you want to find an image of Sabich, these models will not do that. This is a special dish in Israel, right? Also, if you are asking for breakfast images, if this was trained on, different countries have very different breakfast styles, right? So you should start with the basic infrastructure tools, build representations, then build models, and you can do that. And one thing that people observed in language models, not multimodal, is that by training models that have several different languages, you sometimes gain from shared priors, but there is a way to keep both sharing the common things and personalizing the different things.
Okay, thanks.
Thank you.
Other questions? So Gal, one of the emphasis of this conference is about ethical and responsible AI. And I'm wondering if you can say a few words about that with respect to your work, and in particular on possible malicious use of technologies such as the one you've presented today.
I think there are, the usual response is true. With every new technology, you have potential malicious problems. One of the things that people are worried about is deepfake. And usually there are several aspects how to address deepfake. First, it's not the new thing. People could always carefully generate incorrect images, and people have done that years back. With generated images, there are several things you can do. First, it's actually pretty easy to detect if an image was generated. You can train a classifier if an image is generated or genuine. Perhaps it looks the same to our eyes, but classifiers are pretty good at this. The other approach is you can watermark some of the generated content. It's easier than even in language you can watermark some generated text, and in images it's easier. I think this is one of the main concerns. Another concern is perhaps ownership, and I should mention that NVIDIA and Getty announced that they will be releasing models that are built on own data, not crawl data. So every creator and every artist can get paid for their contribution.
Thank you. Great. I have to say this is quite an optimistic viewpoint. Personally, I find as an instructor, I'm often in the need to verify whether generated content is legitimate or not, and I find that increasingly difficult. So it's great to know that in the field of vision, there's some progress in that lines. Any other questions from any member of the audience?
Thanks for your talk. Can you tell us something about the computational cost of these applications and the future applications? Yeah. Power and hardware.
So the original personalization, to train a concept, it would take several minutes on an A100. But there's a way to speed this up. You can train an encoder by showing them a lot of examples of, concept and the target embedding vector. A concept, you train something to give you a good initialization point, and then you can be 100 times faster and train from just like a single image. And this is pretty standard procedure. You often see papers that do a test time optimization process, and then you can speed it up by training a model that gives you a good initialization point for that.
Great, we're out of time for questions. Thank you so much again, Gal.
Thank you so much, everyone.
We adjourn.
Come and talk to me.